Welcome back to Talk Tensors, where we take apart these really interesting machine learning papers.
Absolutely.
And today we're looking at uncommon objects in 3D. And it's all about training AI to see the world in 3D.
Yes. And I think for a long time, the focus has been on just getting bigger and bigger data sets.
Right, more data.
But this paper is arguing that it's not just about how much data you have, but the quality of that data.
So instead of just having a ton of data, you're being more picky about what data you have.
Yeah, you can think of it almost like instead of having a library full of random books, you have a carefully curated collection.
Okay, so you're looking for the best books, not just the most books.
Exactly. And I think the reason for that is because ultimately we want AI models that can work well in the real world.
Yeah, so you're saying if you train an AI model on a bunch of bad data, it's not going to be able to tell good data from bad data in the real world.
Exactly. If you learn to drive in a video game versus learning on actual roads.
Yeah, it makes sense.
There's going to be a big difference.
So how does this data set UCO 3D, how is it actually better than what was out there before?
Well, for one, it's huge. It's over 170,000 scenes and over 1,000 object categories.
Wow, that's a lot.
Yeah. And so it dwarfs some of the previous data sets like CO3DV2 and MBM-GNet. But more importantly, I think it's the quality of the data that sets it apart.
Okay, what do you mean quality?
So they use higher resolution videos, many of them in 1080p or better.
Sure.
And they use a special capture technique called sine wave capture, which I thought was really interesting.
Sine wave capture, that sounds more like a physics experiment than something I'd find in a machine learning paper.
Yeah, it kind of is. So imagine you have an object and you want to scan it in 3D, right?
Yeah.
The traditional way to do that is to put it on a turntable and just spin it around.
Gotcha.
Well, the camera takes pictures, but that can leave gaps in the data, especially for objects with complex shapes.
I'm thinking like one of those little souvenir snow globes.
Yes, exactly.
You can never quite get a picture of what's inside because of all the reflections and the angles.
Exactly. So with sine wave capture, instead of moving the object in a perfect circle, the camera kind of oscillates up and down while it moves in a circle.
Oh, so it's not just going around. It's kind of going like this as it goes around.
Yeah, it's doing a little dance around the object, and that means it captures it from all these different perspectives.
Gotcha. So they're really going the extra mile to capture every detail.
Yes. And they also provide different types of 3D annotations.
Oh, what do you mean by annotations?
So these are like extra pieces of information about the objects.
Okay.
They have point clouds, camera poses, and then something called 3D Gaussian splat reconstructions.
Gaussian what now?
Gaussian splat reconstructions.
I'm going to need a little help understanding what all of those are.
So a point cloud, you can think of it like a digital fingerprint of an object.
Okay.
Where you have all of these points in 3D space that represent the surface of the object.
Gotcha.
And the camera poses tell you where the camera was located when each of the images was taken. And that's really important for understanding the object's position and orientation.
Makes sense.
But the Gaussian splat reconstructions, these are where it gets really interesting.
Okay, let's talk about that.
So imagine capturing the essence of an object, not as a collection of points, but as a set of blurry overlapping spheres.
Blurry spheres. That doesn't sound very precise.
It might sound counterintuitive, but it's actually a really efficient way to represent 3D objects.
Okay.
Especially for tasks like rendering or novel view synthesis.
And rendering, I guess that means creating an image of the 3D model.
Yes, exactly. So it's like a compressed version of the 3D model that still captures all of the essential details.
So you're saying it's kind of like a trade-off between how accurate it is and how efficient it is.
In a way, yes. But what's really impressive is that these Gaussian splat reconstructions are derived from real-world data, unlike previous methods that relied on purely synthetic data.
So it's taking that real-world data and compressing it down into this more efficient representation.
Exactly. And that means that it can capture the nuances and imperfections of real objects, which is really important for training AI models that work in the real world.
Yeah, because the real world is full of imperfections.
Yes.
But they've got all this great data. They're taking these extra steps to get all the detail. But then they also include text captions for each object. Why is that necessary?
Yeah, it's not like giving the AI a cheat sheet or anything.
Right.
It's more like we're teaching the AI to understand the language of both 3D shapes and words.
Oh, so it can connect the two.
Yeah.
Okay.
So by associating text descriptions with 3D models, it's creating this bridge between language and vision.
I guess it's like if you wanted to search for a 3D object and you could just type in a blue vase with a floral pattern.
Yeah.
And the AI would know exactly what you're talking about.
Exactly. And that would be incredibly useful for designers, artists, anyone working with 3D models.
Absolutely. Okay, so this is all really, really impressive, but is this truly a game changer?
Yeah, that's a great question.
To get a better sense, I think it might be helpful to step back and look at the history of 3D object data sets. Like, how did we get to this point?
Yeah, that's a really good point. I think UCO 3D didn't just appear out of nowhere. It's built on years and years of research and development in this field.
Right, of course.
So, like, some of the early 3D object datasets were primarily synthetic datasets like ShapeNet,
Okay.
which was great for learning basic shapes, but it didn't really have the realism of real-world objects.
Then there were data sets like Objaverse, which were massive, but they still relied on, like, artist-created models.
Yeah, exactly.
Yeah.
And those datasets, they played a really important role in developing these first 3D deep learning models,
Right.
but they still had limitations.
Okay.
And the real challenge, I think, was getting this high-quality 3D data from the real world.
So that led to smaller, more specialized data sets. Right?
Yeah, things like GSO and OmniObject 3D,
Yeah.
that focused on particular object categories or capture techniques.
So they were kind of filling in the gaps, but it sounds like UCO 3D is addressing a real need in the field by providing both, like you said, scale and quality.
Exactly. It's bridging this gap between the two,
Yeah.
which has held back 3D deep learning research for a long time. And I think the researchers didn't just focus on the data itself.
Right.
They also went to a lot of effort to evaluate UCO 3D and compare it to existing data sets.
Well, what did those evaluations show?
Well, across a bunch of different tasks, models trained on UCO 3D consistently outperformed those that were trained on other data sets.
Wow.
And that's a pretty clear indication that this data set is not just hype, it's actually delivering real results.
So it's not just bigger, it's better.
Right.
And that has implications for a wide range of applications, I assume.
Yes, absolutely. So the paper highlights 3 key areas where UCO 3D is already making an impact.
Okay, let's hear it.
So there's view 3D object reconstruction, novel view synthesis, and photorealistic text to 3D generation.
Okay, let's start with view reconstruction. Like, what is that and why is it so hard?
Okay, so this is all about creating a complete 3D model of an object from just a handful of images.
So you don't have all the views. You've just got a couple.
Yeah, just a few.
Okay, and how is that challenging?
Well, imagine you're trying to sculpt a bust of someone.
Okay.
But you only have like 3 photographs of them from different angles.
Okay, I can see how that would be a little tough.
It's going to be really hard to fill in all those missing details
Yes.
and create an accurate representation. And it's the same with 3D reconstruction traditional methods. They really struggle to handle those complex textures and shapes when they only have a little bit of information to work with.
Okay, so how does UCO 3D help with that?
Well, the researchers trained a model called light planal LRM on UCO 3D.
Okay.
And they found that it was significantly better at reconstructing objects from these limited viewpoints than models that were trained on other data sets.
Okay, so they're able to fill in the gaps a little bit better.
Exactly.
And why is that so important?
Well, it's really important for applications like robotics and augmented reality, where you often need to understand an object's shape and structure from just a few glimpses.
So you're saying that by using this data set, it can give robots and AR systems a better sense of their surroundings.
Exactly. It's given them more spatial awareness.
That's really cool. All right, so then that brings us to novel view synthesis. What is that?
Okay, so this is about generating a realistic image of an object from a completely new viewpoint,
Oh,
even if that viewpoint wasn't captured in the original images.
so it's like I've taken a picture of this water bottle from a couple sides, and then the AI can like fill in what the back looks like, even though I haven't taken a picture of it.
Exactly. And UCO 3D trained models, they're really good at this.
Yeah.
You can even like hallucinate missing details.
Hallucinate.
Yeah.
What do you mean by that?
It's not as scary as it sounds.
Okay.
It's like, imagine an artist is sketching a scene based on a few photographs, right?
Yeah,
They're going to use their knowledge of perspective to fill in those gaps
right.
and create this complete picture. And in a similar way, UCO 3D trained models, they can use their knowledge of all these different 3D objects.
Right. They've seen so many 3D objects, they can imagine what it would look like from a new perspective.
Exactly, even if they haven't seen it from that angle before.
Wow. Okay, so that's novel view synthesis. And then we have this photorealistic text to 3D generation. What is that?
Yeah, this one sounds straight out of a sci-fi movie.
It does.
But it's becoming more and more realistic thanks to datasets like UCO3D.
Okay, how so?
Well, the researchers use this really clever trick. They essentially reshot the 3D Gaussian splat reconstructions.
Okay, remind me what those are again.
Those are the blurry spheres.
Right, okay.
And
Yeah.
they reshot them from specific viewpoints to create this synthetic data set.
So they're like taking that data that they already have and then creating even more data from it.
Yes, exactly. They're creating a virtual studio to generate these 3D objects.
Wow, that's really cool.
And the results are really impressive. So the models trained on the synthetic data, they actually produced much more realistic 3D objects from just text descriptions
Yeah.
than models trained on purely synthetic data.
So it's like by using this real world data as a base, they're able to make these text to 3D generations even more realistic.
Exactly. It's a major step towards this future where we can just describe something in words and then have the AI create it for us.
That's pretty wild.
Yeah, it is.
Okay, so you've got this massive data set, you've got all this detail, you've got the captions, and it seems like they're doing a really good job of putting it to work.
Yes, they are. And this is like a significant contribution to the field of 3D deep learning.
Right.
But I'm curious, where do you see this research leading in the future? Like, what are some of the novel notions that come to mind when you think about UCO 3D and its potential?
That's a really good question. Well, one thing that I've been thinking about is the potential for using UCO 3D to create a system that could like automatically reconstruct and digitize entire real-world environments in 3D. Well, hold on. So you're not just talking about objects anymore. You're talking about like a room, a building, even a whole city.
Yeah, exactly. Like, imagine being able to virtually walk through any place on Earth captured in like photorealistic 3D detail, all thanks to AI.
That sounds like science fiction. Are you saying that UCO 3D could make this a reality?
Well, think about it. We're already seeing some pretty impressive results with single object reconstruction and novel view synthesis
Right.
using UCO 3D. So what if we could scale that up to entire environments?
Okay, but how would you even do that? Would you need like an army of drones constantly filming everything?
Not necessarily. I mean, we already have so much visual data about the world.
Yeah, that's true.
From smartphones, security cameras, even dash cams.
So you're saying we could tap into this existing data
Exactly.
and use these UCO 3D trained models to like piece together these environments in 3D.
That's the idea. But of course, there would be challenges.
Yeah, I can imagine.
Dealing with varying lighting conditions, occlusion, moving objects, and then there's the whole issue of privacy and accuracy.
Those are some serious hurdles to overcome.
They are, but let's say for a moment that we could overcome them. What kind of impact do you think this would have?
That's a good question.
Mm.
I mean, the possibilities are pretty mind-boggling. Imagine architects being able to design buildings
Yeah.
that seamlessly integrate with their surroundings, not just visually, but also taking into account things like wind patterns,
Right.
noise levels, and even the movement of people. Urban planners could create virtual simulations to optimize traffic flow.
Exactly.
Historians could preserve ancient ruins in 3D.
It's like creating a digital mirror of the physical world.
Yeah, it's a really cool idea, but let's bring it back down to Earth for a minute. What kind of research would need to be done
Yeah.
to even start to make this a reality?
Well, one crucial area is developing AI models that can handle the complexity of these real-world environments, right? UCO 3D focuses on single objects, but we would need models that could understand the relationships between objects,
Okay.
the layout of spaces, the overall structure of these environments.
So it's more like scene understanding rather than object recognition.
Exactly. And then there's the challenge of scalability. Reconstructing a single object is one thing, but reconstructing a whole city
Right.
would require immense computational resources and incredibly efficient algorithms.
And not to mention the need for accuracy.
Right.
I mean, these 3D reconstructions would have to be incredibly precise, especially if you're talking about architecture and engineering.
Yeah, if there are errors in the model that could have serious consequences in the real world.
Absolutely. So it's a big vision
Yeah,
with some big challenges.
yes, definitely. But isn't that what makes research so exciting?
It is. You never know what the future holds.
Exactly.
Okay, so let's shift gears a bit and dive back into some of the technical details of UCO 3D. One thing that really stood out to me in the paper was the use of Gaussian splats. You mentioned earlier that they're kind of like these blurry spheres, but I'm still a little fuzzy on why they're so important.
Okay, so 3D Gaussian splats are a relatively new way of representing 3D objects, and they've gained a lot of traction in recent years. Okay. So instead of representing an object as a mesh of polygons or a cloud of points, a Gaussian splat represents the object as a collection of these small overlapping Gaussian functions. You can think of each of these functions as a tiny sphere with a blurry edge.
So they're kind of like pixels in 3D space.
Yeah, that's a good analogy. And just like pixels can be combined to form a 2D image, Gaussian splats can be combined to form a 3D model.
Okay.
And what makes them so powerful is that they're incredibly efficient to render, especially compared to these traditional mesh-based representations.
And rendering, that's like creating an image of the 3D model, right?
Exactly. So traditional rendering techniques, they involve all these complex calculations to determine how light interacts with the surfaces of a 3D model.
Right.
But with Gaussian splats, that rendering process is much simpler and faster, which makes it ideal for applications like real-time rendering in video games or VR environments.
So it's a more efficient way to create these realistic-looking 3D graphics.
Exactly. And because they're derived from real-world data, they can capture the subtleties of light and shadow much better than purely synthetic models can.
And you mentioned earlier that Gaussian splats are especially good for novel view synthesis.
Yes, they're really well suited for that task because remember, novel view synthesis is all about generating an image of an object from a viewpoint that wasn't captured in the original data.
Right.
So with Gaussian splats, you can essentially reproject the splats onto a new image plane and simulate what the object would look like from that new perspective.
So it's like rearranging the pixels in a 2D image to create a new view. But instead of pixels, you're manipulating these Gaussian splats in 3D space.
Yeah, that's a good way to think about it. And because each splat has that blurry edge, they blend together seamlessly when they're projected onto the new image plane,
Okay.
which creates this smooth and realistic result.
It's really interesting to see how this relatively new technique is already making such a big impact.
Yeah, it really is. It shows how creative these researchers are and their willingness to explore new approaches.
Absolutely. Speaking of new approaches, I'm curious to hear more about how they used Gaussian splats for this text to 3D generation.
Yeah.
You mentioned that they reshot the reconstructions, but I'm not quite sure what that means.
Okay, so this is a really clever technique that uses the power of Gaussian splats to create synthetic datasets.
Okay.
So remember, text to 3D generation is all about training AI models to create 3D models from text descriptions.
Right.
And to do that effectively, you need a huge data set of paired text descriptions and 3D models.
And that's where the reshooting comes in.
Exactly.
Right.
So instead of trying to manually create 3D models for every possible text description, which would take forever and be really expensive,
Right.
the researchers used those Gaussian splat reconstructions from UCO 3D to create this synthetic data set.
So they basically built a virtual studio
Yes.
for generating these 3D models.
They took the Gaussian splat reconstructions of real objects from UCO 3D and then reshot them from a bunch of different viewpoints and generated thousands of synthetic images. Each of these images was then paired with a text description of the object, and that created a massive data set for training text to 3D generation models.
It's a really clever way to use the existing data to create new data sets for different tasks.
It is, and the results are pretty impressive. The models trained on this synthetic data produced much more realistic and detailed 3D models from text prompts than models trained on just purely synthetic data.
Wow. So it sounds like the researchers behind UCF 3D were really thorough in their approach from the data capture and annotation to the evaluation and application of the data set.
Yeah, they were very thorough, and their work is a great example of how this high-quality data coupled with these innovative AI techniques can open up all these new possibilities in the field of 3D deep learning.
This deep dive into UCO 3D has been really interesting. It's amazing to see how this data set is pushing the boundaries of 3D deep learning and paving the way for a future where AI can really understand and interact with the world in a much more human-like way.
I agree. It's a testament to the power of combining high-quality data with innovative AI techniques and the creativity of the researchers in this field.
Before we move on to novel notions, I want to touch on one more aspect of UCO 3D that we haven't discussed yet, and that's the rigorous evaluation and benchmarking that the researchers did.
Yeah, that's really important and often overlooked.
Yeah, it's easy to get caught up in the excitement of these new models and data sets, but it's so important to make sure that the claims are actually backed up by evidence.
Exactly. You have to make sure it actually works.
So they didn't just create this massive data set and assume it was great. They actually tested it.
Yes, they meticulously evaluated UCO 3D's performance on a bunch of different 3D deep learning tasks and compared it to existing data sets and models.
And what did they find?
Well, the results were really impressive across the board. Models trained on UCO3D consistently did better than those trained on other data sets, which really shows how much better the quality of the data is.
So it's not just hype, there's actual evidence to support their claims.
Exactly. And this rigorous evaluation is so important for building trust within the AI community. It's like a seal of approval that says, hey, this is a reliable and valuable resource.
It's a good reminder that scientific rigor is just as important in AI research as it is in any other field.
It is. And it's that commitment to rigor and excellence that ultimately drives progress and innovation.
Speaking of progress and innovation, I think it's time for our listeners' favorite segment, Novel Notions.
Ooh, I've been waiting for this. What crazy ideas have you come up with this week?
Well, this paper got me thinking, about the role of human creativity in all of this.
How interesting. How so?
Well, we've been talking about, all the amazing things that UCO3D can do, train AI to reconstruct objects, generate new views, even create models from text descriptions. It's incredible. But it also makes me wonder, where does human creativity fit into all of this? If AI can do all this, what's left for us?
That's a question a lot of people are asking, and it's a good one. I think it's important to remember that AI, at least for now, is a tool. It can do amazing things, but it needs direction.
Right.
It needs that human spark the vision, the imagination to guide it.
So instead of AI like replacing human creativity, it's more like enhancing it.
Exactly. Think about it like a painter. And their brushes, the brushes themselves don't create the art,
Right.
but they're the tools that the artist needs to express their vision.
Yeah.
And AI is kind of like a set of incredibly powerful brushes for the 21st century.
So with UCO3D, we're giving artists, designers, architects, all sorts of creative people a new set of tools to play with.
That's right. Imagine architects using AI to design buildings that respond to the environment in real time, or artists creating sculptures that defy gravity, or filmmakers using AI to craft these incredible visual effects.
It's almost like we're entering a new renaissance. But instead of paint and marble, our tools are data and algorithms.
That's a beautiful way to put it. And data sets like UCO3D are the foundation for this new era of creativity. By providing this high-quality data and training these AI models to understand the nuances of the 3D world, we're empowering those creative professionals to push the boundaries of what's possible.
It's amazing to think about. Well, on that note, I think it's time to wrap up this deep dive into uncommon objects in 3D.
It has been a fascinating journey exploring all the intricacies of this groundbreaking data set and its implications for so many different fields.
Yeah, we covered a lot of ground, from the technical details of the data capture and annotation to these bigger questions about the role of AI in society.
And as always, we've just scratched the surface. There's still so much more to explore and discover.
But that's what makes it so exciting, right? It's a
Yeah.
field that's constantly evolving and changing.
Exactly. And I think we'll be hearing a lot more about UCO3D and its impact in the years to come.
Absolutely. To our listeners, thank you for joining us on this deep dive into the world of 3D deep learning. We hope you enjoyed it.
And if you want to learn more, be sure to check out the paper and explore the UCO3D dataset for yourself. Who knows, maybe you'll be the one to make the next big breakthrough.
Until next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible with AI.
Goodbye, everyone.